Yes, please.
Great. Okay, so let's go. We don't have much time. Already we spent 10 minutes, so we got just 30 minutes. And I'll send another link after the 40 minutes is expired. I'll send another link. We want to talk about GIS data models and structures. In fact, it's very important that we talk about this because that's the core of GIS. You can compare GIS with CAD systems, AutoCAD, you know, how computer aided design and how the layers are done and all the operations that you can do within such systems. But GIS, the only thing that makes it stand out is going to be the data models and then the structures. Are you okay? Or if you can say models or structures, any of them goes. So GIS data models kind of, you know, we're talking about data models. So we're talking about data structures. So if you take the GIS away, we are dealing with just data models and data structures. In other words, how do we model data? How do we make sure data is properly arranged? Are you okay? That is what data model is all about. Now, what makes GIS special is that GIS is we trying to collect data within our environment, our geography, within, you know, a certain portion of the world. And so such data is always got a locational component to it. Are you okay? In other words, we need to look at the objects around and see how we could, you know, structure them, arrange them so well, okay, in such a way that we can, you know, apply certain procedures and do some analysis on it. So that is the summary of it. And we're going to take our time and look at it and look at the advantages of one model versus the other, because there are basically two data models in GIS. Are you okay? And we need to look at the first one is called the vector data model, and the second one is called the raster data model. So this afternoon, our lecture is all about two things. Are you okay? Vector data model and a raster data model. So not the Rastafarian type of, we are talking about different type of raster here. Are you okay? So the word raster is actually coming from, you know, that those dots that you see on television. Are you okay? So it's coming from electrical engineering and how the television set has these dots, small dots that define the picture that you see on the television screen. That is where the word raster is coming from. It's not rasta. It's got nothing to do with Rastafarianism. Are you okay? It has nothing to do with that. A lot of people hear this word and they're like, wow, what is that? Are you okay? So that is why, yeah, I have to explain it so that you don't, you know, mix it up. Now, what is the raster data structure? What is it all about? Are you okay? So we talk about this raster data structure. Then we'll talk about the vector data structure, VECTOR. And then so let's look at the raster data structure. In the raster data structure, space is subdivided into regular grids of square grid cells. You know, this is like, I don't know, an interesting way to explain something. Are you okay? You take space. Are you okay? The space, let me just say that your project area is subdivided into regular grids or square grid cells. In other words, you have squares and then you divide them up. Are you okay? You have, I mean, divide the whole area into smaller squares. All right. Now you can have other forms of, you know, shapes. In other words, what we are calling the polygonal meshes. A mesh, you know, a mesh is like some kind of, you know, let's look at what is used for, like a net. Think about a mesh like some form of a net. You're right. So we can actually have different ways of subdividing the space. Are you right? And we can have what we call the pixel. In every picture, okay, we have the pixel to be the basic element of the picture. Are you right? Which means that the raster data structure actually is synonymous with what we call a picture. Anytime that you have a camera and the camera takes a picture, you obtain pixels out of it. In other words, the pixels are actually regular grids of square grid cells. So that is why when you buy a phone, then the next thing you ask is how many megapixels? Nobody buys a phone without asking. Why? Because they want to see if the phone can take quality pictures, right? What does the camera do? The camera subdivides the space into regular grid squares. Now, when it does that, then what else happens? Then we need to now talk, we are going to talk about the properties, of structuring data in this format. All right, the location of each cell is defined by its row and column numbers. So just imagine having a regular, so this is what I'm talking about here, having space, yeah, divided into these squares. Are you all right? So we have columns of squares, then we have rows of squares going left to right. Okay, and we are saying that the location of each cell is defined by each row and column numbers. So it's like matrices. Every civil engineering student who's at level 400 knows something about matrices because we've done a lot of maths. So we can now define a particular cell by its row and column numbers because all the regular grid squares have been arranged in rows and columns. Are you okay? So for example, when you look at the first cell on the top left corner, okay, will now be 1, 1, kind of. Are you okay? And then as you go to the right, then the column numbers are increasing. And as you go down, then the row numbers are also increasing. Okay, so the location of each cell is defined by, you later find out that the vector data structure or data model is a bit different. It doesn't work that way. So let's take note of what is unique about this one. It says the area that each cell represents defines the spatial resolution of the data. In other words, the cells are actually indicative of how fine our image is, the image that has been captured. Are you okay? So if we have a smaller cell, the smaller the cell size, the finer the resolution, the better the image. Also, are you okay? Because then we can clearly distinguish between objects within our study area and within the space within which we are actually working. So each cell actually represents or defines the spatial resolution of the data. I think it's not really well written there. The area that each cell represents, okay, defines the spatial resolution of the data. So the word resolution there is actually telling you how good the data that you have, how accurate, if how precise the data that you have is. So let me give you a practical example. A practical example is a satellite moving across a particular area on the surface of the earth and taking an imagery. Anytime you watch CNN and watch BBC, we see satellite images being shown to us all the time. That maybe there's a nuclear warhead in Iraq that has moved by a few millimeters. Why? Because nuclear warhead, they said that they want to launch it and kill someone. That image, the satellite images that the meteorologists and all these people are using, weather forecast people are using, all these things are actually based on the raster data structure. In other words, regular grids of square grid cells are being used. And there's a device. Okay, the device normally is a camera. So on a satellite, then you could have a camera mounted on it. So recapping, last week we were talking about data sources. Are you okay? How to acquire data. And we talked about remote sensing. Remote sensing will be one of the sources of raster data. Okay. Now, if you all can hear me, if you don't quite follow, you can always, let me know. I will explain further. I know sometimes it may not come so easy to you, but if you understand too, I'll be very happy. I'm so excited when you understand me. That means I also get to ask you questions, not too difficult questions, right? Okay, so let's talk more about the raster data structure. The position of a geographic feature is only recorded to the nearest pixel. In other words, once the device has actually divided or tessellated the space, covered the space with regular grid squares. Are you okay? Then the next thing is that we need to now find out where an object is. And we are saying that the position of geographic feature is only recorded. So we are recording the position of geographic features, which is what the model is about. We are trying to model our world. Are you okay? We are trying to make sure that there's a structure to the way things are. Are you okay? We are collecting data in a structured way. Now, the second one, the next one is there's value stored for each cell indicates the types of the object, phenomenon, or condition that is found in that particular location. So when I get a satellite imagery and I see a red square region or a red rectangular regular shape, which is actually filled with a color red, it's a dirty red. I'll start thinking, is that the roof of a house? Because most people are now using red, red roofs, roofing. The roofing of most houses are now looking like, red or maybe blue. Sometimes green too. It depends on the color that you want to go for. Okay, but the natural objects, natural features that we find normally are not regular in shape. For example, when you find a river, it's not regular. Are you with me? But then the value to be stored in red, naturally, you won't find things that are red, of course, unless it's a bare soil with some elements of iron in it. Then, of course, in that case, the ground will be looking reddish. But I mean, I haven't even seen one before. I've been to the farm and out there, but I haven't seen. But the point being made is that the value for the cells, you see, so we divided the area into regular cells, and then every object is being recorded at the location of the cell, the nearest cell, okay. And then the value of the object being found there is being recorded. Now, this value can be just the color of the object. It can also be, for example, the temperature of the object. It can be the height value at that point. Are you okay? All right. So now we're saying that different types of values can be coded. So you see, we are trying to store the value, but we can store it as an integer, as a real number, or we can store it as alphabets. As long as we can have what we call a lookup table, which allows us to now see that, okay, when I see A means bare soil, B means, okay, vegetation. Then in that case, we don't have to even worry about it, how we code it. But usually integers, real numbers, and alphabets, they are used to code it. So in the table that I just showed you, I revisit this table several times. You can see here that 1 stands for forest. So when I see the number 1, it's a forest. So you can see 1, forest. When I see 2, it's cultivated field. Are you with me? All right. So now this is the raster data structure, raster data model. This is how data is being captured. So the square over there, we are saying that in that small cell, everything in there is a forest. Are you okay? And usually resolution, and this is what we call resolution. There's the resolution of an image. And if you actually listen to me carefully from last week, the data sources lecture, and remote sensing, I talked about resolution, spectral resolution, and spatial resolution. So here you can see the direct link. Are you okay? That the size of that cell now is determining what can be the smallest object that can be seen in the image. Are you okay? All right. So if you don't even get this whole thing, think about the pictures that you've been taking with your phone. Okay? Compare your megapixel with another friend's megapixel. If you have 12 megapixels, that's 12 million pixels. In other words, you divided whatever object that you are taking a picture of into 12 million pixels. Now, the smaller the pixel, the clearer the image. So when you buy a phone with, say, 20 megapixel, obviously it will cost twice as much as, say, 10 megapixel, just for the quality of the picture. And I guess that's why the iPhones are costing so much. Are you okay? All right. So this is a concept. The data structures is a whole topic in information technology. You need to appreciate the one that we are dealing with right now. Okay. So we talked about the lookup table. So that's the lookup table over here. Okay, this small table we see here. All right. So it's required to more or less interpret the values that are being stored. We are modeling our world. Okay, we are trying to get it into the computer. Remember that we are trying to get everything around us, all the forest. on one computer in your office in Accra, somewhere in a corner, or in Tamale or somewhere. And then you can now say, okay, there are some fires going on here without you going there, flying over there. Like I see, that's what the system is all about. Different attributes at the same cell location are stored as separate themes or layers. So guys, we talked about themes and layers. We talked about the overlay. Remember that, okay? You never know, that might even come in your midsummer. I'm going to have to give you something to do for your midsummer. Okay, get ready for it. But we've talked about this already. So different attributes at the same cell location are stored as separate themes or layers. Anybody who's been in this class should, you know, I mean, you can say you've forgotten, but honestly, I know I have taught you. You should know that. I know that you know, okay, what themes and layers are. When we have several values at the same location, we layer them, we stack them. Are you okay? And later we can operate, we can have overlay operations over them. We can have union overlay, intersect overlay, symmetric difference. I hope you remember all that. So this statement here is just a repetition of something that we've already heard before. Okay, let's see more about raster data model. It says separate themes or layers. For example, raster data pertaining to the soil type, forest cover, and slope covering the same area. So we that's what we are actually talking about. These are examples. Are you okay? So we can have soil type. So soil type, talk about clay. Clay. Or is it clay? Yeah. What is this area? Is it loamy? What is this area? Is it sandy? All right. You can have that at one level. Okay, on one layer. Then you can also have another layer for the same place, that same location. Forest cover. Do you have forest vegetation or not? Are you okay? Okay, you can look at slope too at the same location. How is this place sloped like? Okay, all right. Like I said, you can even add more to it and start looking at which constituency do we have this. Okay, and then etc. Of course, you can extend it. It goes as far as you can. All right. So now we have to note one thing, that it does, we don't have to necessarily use square grid cells. It doesn't have to be squares. Like as you can see in this image, these are squares. We can think outside the box and look at dividing the area rather into triangles. Okay. So when we do that, for example, then we are dealing with what we call one of my favorite, models, the irregular tessellation. So tessellation means like covering the area. It's an English word, please. We are in university, so as for the words there, we're meeting also the words. All right. Example, the triangulated irregular network. In other words, what we are saying is that the area has been divided into an irregular network. In other words, you end up also having, triangles. And when you do that, in fact, most of the cartoons that you've been watching, cartoons are really virtual, isn't it? They don't really exist. Are you okay? But all the terrain most of the terrain used in most of these gaming, engines and all that are actually making use of the TIN model, or the triangulated irregular network. Are you okay? All right. So we can also have the hierarchical tessellation, but ignore that cut tree and all that. These are different ways of representing the 3D surface. Are you okay? Everything that we are doing is within the surface. So now this is a typical, example or image. The triangular irregular network. You can see that surface. If you really, really look at it well, you can see this is a surface. It's as if you can walk on it and get to a certain point. But really, you are just being deceived. Really, it's just triangles that are joined together. Are you okay? All right. Great. So basically, that is the raster data model. If you don't seem to follow me and you're a bit confused, you can ask me. But what I want you to know is that everything that I'm talking about is a representation of your world in the computer. Are you okay? But in this case, it's the data model, modeling data, modeling your world through data. Are you all right? Okay. Any question can come at any time. Otherwise, I mean, in the next 5 seconds, I'm just moving on. And I'm going to talk about the next model, the other model. In fact, basically in GIS, we have two data models. We have the vector data model, we have the raster data model. When I'm teaching you like this, a lot of people don't pay attention, doing their own thing. You know, you even ask, sometimes you ask students a simple question: what are the two data models in GIS? They're talking about something else. But this class is different. I know you are paying attention. All right. Okay, so the vector data model. What's a vector data model? What is it on about? The vector data model actually represents the world, are you okay, as points, lines, and polygons. So instead of you actually tessellating the area with regular gray squares, we're simply gonna see every object to be a point, a line, or a polygon. Are you okay? All right, great. So let's move on. Now it's very important for you to realize that this is also known as the fundamental geographic primitive. Doesn't matter.
Good afternoon, sir.
Hello, how are you?
Fine, sir. Sorry I'm late, sir.
It's fine.
Okay.
Okay, sit down, please. All right.
Okay.
So points, lines, polygons. So we can actually look at representing a tree as a point and not as a line. Or you can represent a river as a line and not as a point, because a river is kind of linear, it's extending in a narrow way. Are you okay? You're right. It looks like a river looks more like a line. Are you okay? But some rivers, you know, really expand, and sometimes you wonder whether it's a line or it's a polygon. Are you okay? All right. So a lake can be represented as a polygon. This is very simple enough. I think we can all, you know, understand this. All right. We can look at soil classes, clay and other as polygons. If you want to represent that on a large tract of, you know, farm, then you can look at that. We can represent rail lines, transportation systems as lines and not as points, because they seem to be traveling from one point to the other, and they are narrow in their extent. They don't expand. They're not really, you know, like regions. They are not regions. Are you okay? All right. Now let's take note that every line is basically made up of points. Every, you know, polygon is made up of lines. Are you okay? All right. So there's that connection. I see it's bringing us back to a certain topic, topology. Hope you all remember that. Okay. So now let's start interconnectivity and relationship between points, lines, and polygons. So every object that I give you, you should be able to tell me how you model it, whether as a point, as a line, or as a polygon under the vector data model or vector data structure. The structure is what's implemented in the computer. Are you okay? So this is how the computer actually stores vector data in the computer. Each point is stored by its location, X, Y, that's the coordinates, together with the table, the attributes of this point. Are you okay? So in other words, when you look at this table, the point number 1 is actually stored at a location 7, 6. Are you okay? So this is like a graph. For you to understand, this is how it works. But on the ground, these values are quite huge. So surveyors deal with these XY coordinates. I keep saying it, they are very huge numbers. 75000 something feet. Are you with me? In reality. But this is for you to understand the model. Are you all right? So 1.1 is stored 76, the coordinate. 0.2 is stored 1, 4. It's a coordinate. Are you okay? So you can see that there's a table. So the computer has to store it that way. Now, when you look at this other table below, you can see that here we are storing the attribute of the point. And of course, now we are linking the two tables somehow. So that 0.1 has a depth of 12.35 and then a certain amount of 63 or whatever, 63.45. What we are saying is that now we can really have a big table which actually lists all the attributes to be found at the certain location 1, 2, 3, 4, 5. Okay, I think this is very simple and easy enough. You can look at a line a line is actually made up of points, or if you like, nodes or vertices. Are you okay? So topology is somehow coming in there. So when we look at line number A, so we look at this one, A, 1 to 3. Are you okay? So first node is 1, the last node is 3. So here we are almost getting into topology. Are you okay? And then we can now look at point line A and then associate an attribute with it. So this could be a pipeline network. Are you okay? I want to actually look at the pipe capacity. Are you okay? In terms of whether centimeter cube or whatever. Then the flow, the units of the flow has to be stated in the metadata. I hope the class is following because I've talked about metadata, data about data. Are you all right? So that is why you wouldn't know. You'd be asking yourself, what units are these? And that's where you find that the metadata. So you need to, that's why metadata is essential for our data creation and data acquisition and everything that we do in GIS. Are you okay? But obviously, I want you to just ignore the fact that the line is made up of the nodes. Line A is made up of nodes 1 and 3, right? In between 1 and 3, we could have had vertices going on there. But of course, we don't need that. Then we can have the last table in these 3 stack tables. The last one below, the lowest table is actually having the attributes. Are you okay? Now remember that when it comes to attributes, nobody's going to really say, let's learn some attributes. Everybody, at the university level will know. When I say give me the attributes of a road, you should be able to tell me, it can be like 5 or 6 or something like that. Are you okay? We don't teach that. When you teach GIS, you don't teach people. So I'm expecting that you will know some of these attributes and you can identify with it. Are you okay? So that is the line. The storage of the polygon is also similar to the line and then the point. A polygon is represented by a closed sequence of lines. Are you okay? A closed sequence of lines. So it has to be closed per the topology rules. It has to be, and also by definition in dictionary and by whatever we learned in primary school, a polygon has to be closed. If it's not closed, it's still a line. It's in fact, it's what we call a polyline. Are you okay? A set of lines joined together.
Okay, sir.
But they have to necessarily close. Now, when you look at it, then the polygon is also made up of a sequence of nodes. Okay, so in this particular example, polygon A is made up of nodes 1, 3, 4, 2, and 1. And then the small tables down there, okay, has the attributes. Okay. So the whole idea of putting data into tables is that they can be joined. Put it in your mind. In fact, you gradually, once we learn in GIS, you are learning several technologies. There's IT. So you see here, you can see databases. Some concepts in databases are coming up here. Okay, you can see the joining of tables happening here.
Yeah.
So I want to encourage you to read. Yeah, read. University, that's how it's all about. Don't sit down. The lecture is supposed to help you get more excited about it, but read around and then you get more understanding. Okay, so the vector data model and structure, we can have several implementations of it. Is that okay? What it means is that you see people are coming out doing research, trying to find out how best to represent the world. Are you okay? Someone said raster, vector, and then someone said that even with the vector, you can have the spaghetti type of vector where all the data you have, like a surveyor going out to the field and picking so many points, it wouldn't make sense. That's the spaghetti vector model. Okay, it's limited because everything is points. Meanwhile, there are a lot of polygonal objects, lines, and all that in those points. Unless they are joined up, that's called spaghetti vector data model. You can have the hierarchical vector data model. Are you okay? All right, and that also allows you to actually look at data or structure it in a hierarchical manner. Parent-child relationship. Are you okay? All right, so there's a whole lot of inheritance and all that. Those concepts also work. But just put it in your mind, okay, that we have variants, let me just say, different implementations of the vector data model. At the end of the day, It's points, lines, and polygons. Okay, basically.
Okay, sir.
All right. So now let's take a few notes. A vector data structure that aims at retaining spatial relationship by explicitly storing adjacency information. Then we're looking at topology, a topological structure. Are you okay? All right. So topological model. Are you okay? So instead of having hierarchical vector data model, spaghetti data model, then we can have the topological data model, that kind of thing, you know. But at the end of the basics are lines, points, and polygons. Are you okay? All right. So I think we talked about the fact that nodes are the beginning and the end points of a line in the vector data. And obviously, topological information is stored by looking at from node to node, etc. Left polygon, right polygon, to ascertain the direction. Are you okay? Remember that we talked about contiguity as a, you know, one of the rules in topology. Are you okay? All right. Great. Let's move on. So spaghetti vector data model, that's an example. And then the hierarchical vector, I don't want us to, you know, spend too much. I'm not going to ask you to look deeper into it. So just take note of it. I'm skipping them somehow. I'm your examiner. Is that okay? So you can look at these, but just don't waste your time on it too much. All right. So the vector data model versus the raster data model in pictures. So now, if you don't even understand everything I'm talking about, since we started this 135 or something that we started this lecture, this picture should not explain everything. Are you okay? This is like a summary. There's this area, okay, that we are working on. We want to represent that same area using vector on the left and then raster on the right. Are you okay? So you see the raster has divided the area into squares, regular grid squares, and then he's storing value for every square. And the values are in alphabets, not integers. Could have been integers. A, B, C, D. So when we see A, we know A, it means we have clay. E means we have the, are you with me? Soil type.
Yes, sir.
Geology. Could have been geology. Could have been anything. Let's